In this lesson, we will discuss limit laws. These are precise laws that allow us to evaluate limits. Let's see how this works in example 1. Let's assume that these two limits exist. The one as we approach 1 of f of x is equal to 5, and the one as we approach 1 of g of x is equal to 4. Can we use this information to figure out what this limit is equal to? The limit as x approaches 1 of 2 times f of x plus g of x. If you look at this, you might think, well, I think I know what the answer is just by guessing. As x goes to 1, f of x goes to 5, and then g of x goes to 4, can we simply just plug those numbers in and get the following answer? 2 times 5 plus 4, which is 14. And the answer is yes, this is actually the value of the limit. So here's a really fast way to compute a limit. But why are we allowed to do this? Well, there are laws that say we can take this approach to getting our answer. I'm going to state 2 of these laws. There's 11 in total, and then we'll see how they work in this problem here. The first limit law that I'll state, I'll call it limit law number 1. It says that if you take the limit as x approaches some number a of the expression f of x plus g of x, where f and g are any two functions, if the two limits individually exist, you can write this as the limit as x approaches a of f of x plus the limit as x approaches a of g of x. You can think of this as basically distributing the limit to both terms, or if you see a sum, you can break it up into the sum of limits. There are, like I said, 11 limit laws in total, which I'll state on the next slide. The third one on that list, which I'll write down here, says, if you look at the limit as x approaches a of some constant c times f of x, if this limit of f exists, we can write this as c times the limit as x approaches a of f of x. Essentially, you can factor this constant c outside of the limit. How do these two laws help us prove that this limit here is equal to 14? Well, let's run through this argument one more time, but by using these two rules. So starting over, we have the limit as x approaches 1 of 2 times f of x plus g of x. Since these two limits exist individually, I can break this up into the sum of two limits by putting the limit here and the limit there. So here I'm using the first limit law. This says the limit as x approaches 1 of 2 times f of x plus the limit as x approaches 1 of g of x should be equal to what we started with here. So this is now this because we used the first stated limit law. To complete this, this is set up. I know this thing is just going to be equal to 4. Here, I see there's a constant that you can actually factor out of the limit, and that will be my next and final step. I can take out the 2 and write down the limit as x approaches 1 of f of x plus the limit as x approaches 1 of g of x. This is equal to 5. This is equal to 4. I'll simply plug those in and write this as 2 times 5 plus 4, which, as we said, is equal to 14. And again, the last step we did here was I used the third limit law to go from this step to this step. So this is a lot of work to verify that the answer of this limit is 14. Eventually, we want to get to a point where if you see an expression like this and you want to figure out the limit, we just want to plug in numbers to get our answer if possible. So let's look at these laws, all of them that are stated on the next slide. If you assume that c represents a constant and that both the limit of f and g exist as we approach a, then these 11 laws or rules are true. And the ones we used in the previous example were Rule 1 and Rule 3, where you can break apart the limit over a sum and then factor out constants from the limit. There's a law for taking the difference or a product or a fraction, provided that the denominator is not equal to 0, as well as these other laws here. So you do not have to memorize these. Basically, we just have to know when they can be applied. And once we become comfortable with them, we really won't reference them at all. So like I said, there's 11 here. I think I want to take a closer look, though, at Law 8 and 9. This one says the limit as x approaches a of a constant is actually just the constant. And Law 9 says the limit as x approaches a of x for some reason, is just equal to a. If you have an intuitive feeling for why these are true, that's fantastic. On the next slide, what I'll do is state these two laws and justify why they are in fact true. So the eighth law stated that if you take the limit as x approaches any number a of a constant, that is equal to the constant itself. So for example, what is the limit as x approaches 2 of the number 5? Well, according to this law, the answer should just be the constant 5. The reason this is true is because the function that we're working with, f of x, is actually the constant itself, 5. If you try to figure out this limit by looking at a table of values, x versus f of x, you want to approach 2 and then look to see what the limit becomes. I'll approach 2 by going 1.9, 1.99, and then 1.999. In this function f of x here, as you get closer to 2, the output is actually always just the number 5. It's always the constant itself. So I can see from this table, it just stays 5, and therefore that's why this limit itself is 5. There's nothing special about using 2 or 5. It could have been any number here and here, and that's why this is true as a fact in our limit laws. If you compare that to the ninth limit law, which was the limit as x approaches a of x is equal to a, why is this true? Intuitively, it looks like, well, you could just put a in place of this x, and that would be your answer. If you want to look at something more like this to justify the reason why, what I'll do is use an example. What is the limit as x approaches 4 of x? According to this law, the answer should be 4. Why is this true? Well, if you let f of x equal the function, which in this case is x, and you look at a table of values where we'll approach 4, what happens to the y values? I'll approach 4 by going 3.9, 3.99, and then 3.999. The output is actually going to be, well, if these are the x values and my function is x, you actually just get the same numbers here that you have here. So when you plug in 3.9, you get 3.9 back. You plug in 3.99, you get that back, and the same thing is true for 3.999. As these are getting closer and closer to 4, so are the y values, and that's why this is the answer here to this limit law. Again, there's nothing special about using 4 and then x here. The answer is just going to be 4. So just to restate this, all of the limit laws on the previous slide are not to be memorized. They're to be referenced in order for us to prove that certain limits exist. So let's one more time hear an example to apply limit laws to figure out this limit and this limit, if they exist. And here again, we're assuming the limit as x approaches 1 of f of x is 5, and the limit as x approaches 1 of g of x is equal to 4. Let's start with this one here. So here I have a limit of a fraction. Well, there's a limit law that says if the denominator is not 0, you can break this up into the limit in the numerator and the denominator separately. So I'm going to write that out. This is equal to the limit as x approaches 1 of the entire numerator, which is f of x plus x. And that's divided by the limit of the denominator, the limit as x approaches 1 of g of x plus 3. Thinking ahead here, since g of x goes to 4 and 4 plus 3 is 7, this denominator is not 0, so this step should be valid. Here we used the fifth limit law to justify this. Okay, now in the numerator and the denominator, we have a limit of a sum, and both parts of the sum exist within the limit, so we can split this up as follows. Within the numerator, you can say, I see there's a sum of limits. This is equal to the limit as x approaches 1 of f of x, plus the limit as x approaches 1 of just x. And we can do the same thing in the denominator. There's a sum, and we can split this up as limit as x approaches 1 of g of x, plus the limit as x approaches 1 of just the number 3. So here we actually just use the first limit law, and we use that a total of 2 times. Now the last part of this is, oh, well, this is given information. This limit is equal to 5, so I can just put a 5 here. This limit is equal to 4, so I can put 4 here. I'll just plug those in my next step in my fraction. So it's going to be 5 plus the limit of whatever this is, divided by 4 plus whatever the limit of this is. We talked about rules 8 and 9 on the previous slide, and that's what we can use to figure out this limit and this limit. This is a constant, so its limit should be 3. I'll write that down. And since this is just x, we can put the 1 in place of x and put a 1 here. I'll just note that we use limit laws 8 and 9. And here we go. This limit is equal to this number, which I'll write as 6/7, and that is the final answer. So that's carefully justifying that this limit is equal to this using all of the limit laws that we have. In retrospect, you probably could have looked at this and said, nothing will go wrong if I just plug in the appropriate numbers, a 5, a 1, a 4, and then just leave this as 3. That's the fast way to get the answer, and at some point, that's the approach we're going to want to take. All right, let's use limit laws in this example one last time here. Does this limit exist? Well, thinking ahead, if you put 5 here, the top's 5, if you put a 4 in place of g of x, you get 4 minus 4, which is 0. I think it's going to turn out that this limit does not exist. If you try to use limit laws to justify this, you'd have to use the fifth limit law, which has to do with fractions. This is equal to the limit as x approaches 1 of f of x divided by the limit as x approaches 1 of g of x minus 4. But actually, unfortunately, the fifth limit law does not apply. You can't go from this first step to the second step. And the reason is the denominator, if you look at the limit as x approaches 1 of g of x minus 4, that's going to be equal to 4 minus 4, which is 0. So your denominator cannot equal 0. In fact, if you examine this fraction, as x approaches 1, this becomes 5 divided by 0. That is a number that does not exist. If you want to be more specific, you can say that in this function here, this fraction, as you get close to 1, your fraction looks like this. This is enough to say that at x is equal to 1, there is a vertical asymptote on the graph of f of x divided by g of x minus 4. I don't know what the formula for this function is, but if your expression looks like this, there must be a vertical asymptote. This is enough to say altogether that for this limit, it does not exist. All right, let's now introduce a limit law that will really speed up this process. Basically, if you want to find the limit as x approaches a of f of x, when can you simply just take the number a and put it in place of x to get your answer? Well, according to this law here, if you have a function f, and the number a is within the domain of this function, meaning it's not at an endpoint of an interval, if f is any of the following functions, or sums, differences, products, fractions, compositions, if it's anything that looks like that, you can simply put the number a into the function itself to figure out the value of the limit. It's basically every function that you are familiar with. Polynomials, rational functions, exponential, root, logarithmic, trigonometric, and inverse trigonometric. Just to get a feel for what those look like, I'll write an example of each one down. So polynomials, those are things of this form. Maybe something like x to the fourth minus 3x squared plus 1. So lines, quadratics, fourth powers, fifth powers, and so on. Rational function means ratios of polynomials. So those are fractions where you might have something like x plus 1, a polynomial in the top, and then in the bottom you have a different polynomial, maybe something like 4x cubed plus x. If you see a function like this, and the number a is in the domain of this function, to figure out the limit, you can just put that number into the expression. Exponential functions, so things like 2 to the x or 3 to the x. In fact, if you were to add or subtract these two together, that would work as well. So again, not just the functions themselves, but sums, differences, products, fractions, if there's compositions. A root function might be something like, here's the square root of x, maybe we could subtract the cube root of x from it. So functions like this. Logarithmic might be something like the natural log of 3x plus 1. And here, 3x plus 1 is composed within the natural log function. Trigonometric are things like sine, cosine, and tangent. So you could see something like sine of 3x plus pi. And then inverse trigonometric would be things like arcsine, arctangent. And so I'll write down, you can write two ways, tangent inverse of x, or you could just say arctangent of x. This is an inverse of a trigonometric function. So if you see any of these, or if you see them added, subtracted, multiplied, and divided, or composed, we can simply, on the domain of that function, put the number in place of f to get our answer. Let's see how this works in example 3. I want to figure out the limit as x approaches 4 of the square root of x plus 7 minus sine of pi x. Well, here's a root function. This constant function you could think of as a very simple polynomial. And then we're subtracting a trigonometric function, which has a composition in it. The number 4, you can put in place of all the x's and get a number back. For that reason, you can simply state that, oh, well, this limit is equal to the square root of 4 plus 7, then minus sine of, if you put 4 in place of x, you get pi times 4, which I'll just say 4 pi. That's it. That's the value of the limit. You can simplify it. Square root of 4 is 2 plus 7. Sine of 4 pi is 0. And this whole thing is just equal to 9. So that's very quick. If possible, this is the approach to take. Let's try one more. This thing here, this is a rational function. If the number 3 is in the domain of this function, we can simply put 3 in place of x. The only number that causes an issue is 1, and this is 3. Therefore, I can simply say this limit is equal to 3 squared minus 1 divided by 3 minus 1. 3 squared is 9. 3 minus 1 is 2. 9 minus 1 is 8. And our answer is 4. So it's very fast. If possible, this is the approach to take. Okay, let's put all of these ideas together here in example 4, where I'd like to figure out this limit. Notice this is the same function as the previous example, except instead of a 3, there is a 1 here. Can I simply take the number 1 and put it in place of x to get my answer? Well, we can try. We can say, oh, well, this would be equal to 1 squared minus 1 over 1 minus 1. 1 squared is 1. 1 minus 1 is equal to 0, and we get 0 over 0. And this is an undefined expression. Does this mean the limit does not exist? Well, this is 0 over 0. It's not a non-zero number over 0. Therefore, I don't know if there's a vertical asymptote on the graph of this function or not. That means this limit might actually exist. Unfortunately, we cannot take this approach to figure it out. It didn't give us anything useful. It's no good. Let's take a different approach here. In trying to figure out this limit, the trick is going to be to simplify it in a way so we'll have a new expression to plug a number into. And I'm seeing in the numerator we have x squared minus 1. We can factor that thing. So let's see what happens if we do that. This is the limit as x approaches 1 of, I'll write the denominator as x minus 1 and put some parentheses around it. In the top, this is a difference of squares. We can write it as x minus 1 times x plus 1. This limit is equivalent to this because these two expressions are equal. And what you can notice is, hey, the x minus 1s can cancel. We can write this as the limit as x approaches 1 of just x plus 1. So this limit is actually equal to this limit. Now here, if you check out this limit, you can actually just directly plug the number 1 in place of x to get your answer. This follows from the previous theorem. That is, this is equal to 1 plus 1, and that's 2. So here, this limit, if you first try to directly substitute 1 into the function, you get 0 over 0, which means nothing. But if you take this approach, you actually get that this limit is equal to, meaning it does exist. I'd like to point something out with this expression and the thing we wrote here, which is x plus 1. I'd like to note that x squared minus 1 divided by x minus 1, if you write, is that equal to x plus 1, this is actually a false statement, like this thing here. This is not true. And the issue is the number 1. You can put the number 1 into this expression, you get 2, but you cannot put the number 1 into this expression because you get 0 divided by 0. So the number 1 is a problem in saying that these two things are the same. So these are like almost always equal. It's just that this number causes an issue. Even though these things are technically not equal everywhere, why are we allowed to, in this limit, say, well, this thing is equal to that thing? The reason is, when we defined a limit, we said we approach the number but never actually use it, like in the table of values, to get our answer. That's the point of leaving out the number itself when we originally defined a limit. It'll allow us to make a statement like this. This expression is equal to this one. Continuing with example 5, let's compute this limit. Can we simply take -3 and put it into all the x's to get our answer? That's a good first step. Let's check it out. That's -3 squared minus 2 times -3 minus 15 all over -3 squared plus 7 times -3 plus 12. The top is going to be 9 plus 6, which is 15 minus 15. And then we have 9 minus 21 plus 12. That is 0 over 0. So unfortunately, this approach did not work. This limit may or may not exist, but we just can't do it this way. At this point, one thing to point out is we're probably going to factor this and cancel a common factor between the numerator and the denominator, just like in example 4. Here's something to look for. The number you approach, which is -3, I'm expecting to see an x plus 3 show up somewhere within this process. The reason is if you put a -3 in place of x, you get -3 plus 3, which is 0. In fact, I think there'll be a 1 on the top and the bottom. That's why you end up with a 0 over 0. There should be some expression that makes the equation equal this. Let's see. To solve this problem, I'm going to factor the numerator and the denominator. Okay, if I factor the numerator, it should get like a couple of pieces. Same thing with the denominator. Hey, what do you know? In the top, this is x plus 3 times x minus 5. The reason we got a 0 here is because, oh, there's an x plus 3. And if you put -3 in place of x, that makes it 0. What about the denominator? Also an x plus 3. That's x plus 3 times x plus 4. So this expression is equal to this one. And we can cancel the x plus 3's. And this, in a limit, as we approach -3, is equal to x minus 5 divided by x plus 4. And I'll just leave off the parentheses because I don't need them at this point. -3, I can simply substitute that in place of x because this will equal some number. I get -3 minus 5 over -3 plus 4, and this is -8 over 1, or simply -8. So again, just to briefly state, this fraction by itself, technically it does not equal this fraction by itself. If you exclude the number -3, then these two things are equal, and that's why we're allowed to use this approach to get our answer. In example 6, we want to figure out the limit as t approaches 4 of 1 over t minus 1 over 4, all divided by t minus 4. If we try to simply put 4 in place of t, we get this expression. A fourth minus a fourth is 0, and 4 minus 4 is also 0, and this did not work. 0 over 0 does not exist, but the limit may still exist. I see that I'm approaching 4, so I'm kind of thinking ahead that, oh, well, I want to at some point cancel the factor t minus 4. Like, I want that to go away. The t minus 4 is why we get a 0 here, because if you put 4 in place of t, you get 0. So how do we simplify this expression in a helpful way? I'm going to try to get rid of the fractions within fractions. I'm going to use a trick for that. I'm going to use the least common denominator for the fractions I see, which are here and here. not the main fraction, but the individual ones. I have a t and a 4. The least common denominator is 4t. Therefore, this limit that we started with, this thing here, is equal to the limit as t approaches 4 of, I'll put 1 over t minus 1 over 4 divided by t minus 4. And I'm going to multiply this by 1, which means I will not change the value of the fraction. But I'm going to write 1 as 4t divided by 4t. Clearly, this is equal to this because this equals 1. Multiplication by 1 does not change the value of what we start with. I'm going to want to multiply 4t to both of these terms, so I'll include some parentheses in the numerator. I will put some parentheses in the denominator as well, but I'm not going to distribute this 4t to both terms. The reason is I want to cancel this thing at some point, so I'm going to leave it factored out. So I'll first take 4t and multiply it here, and I'll multiply 4t here. I'll put that in my next step down here. This is the limit as t approaches 4 of. When you multiply 4t here, you have 4t over t. The t's cancel, and you're left with the number 4. Then we have minus 4t here is 4t over 4. The 4's cancel, and you're left with the t. In the denominator, I'm simply going to just leave it as t minus 4 times 4t. Again, I'm not going to distribute this in because I want to cancel this thing. And if you look at this, it's almost equal to the numerator. It's just that it looks backwards. The negative here is in front of the t, and here it's in front of the 4. We should be able to cancel these. What I'm going to do is factor the negative out of both terms in this expression. It'll make this look more like this, so we can cancel it. In my next step, I'll put the limit as t approaches 4 of. I'm just going to leave the denominator alone. It's this. In the top, if you factor out a negative, that means this 4 has to be negative 4 now. And this minus t has to be plus t. And the reason is, if you multiply the negative back in to reverse this step, the negative negative makes this positive, and the negative positive makes this negative. I'll write it again, but I'll put the t first and the negative 4 second. So that'll be my next step. I'll continue this here. That is the limit as t approaches 4 of. So that's negative t minus 4 divided by t minus 4 times 4t. And now we can cancel that with that. What's left over in the numerator is the limit as t approaches 4 of, well, that's really negative 1 divided by 4t. That was a lot of work, but this in a limit is equivalent to this. Can we just plug 4 in place of t to get our answer? Definitely. 4 times 4 is 16. So I'll just say my next step is put 4 in place of t. This is negative 1 over 16, which I'll write like this. That's the answer. In example 7, I want to figure out the limit as h goes to 0 of this fraction. I'll note that, well, we can't put 0 in place of h. We can try it. We'd get the square root of 1 plus 0 minus 1 all over 0. That's the square root of 1 minus 1 over 0, which is 1 minus 1 over 0, which is 0 over 0. No good. This approach did not work. In fact, if this limit exists, for us to figure out the answer, we're going to have to cancel an h from the numerator and the denominator. I'm expecting h over h to be somewhere in our process if I can figure out what this limit is equal to. The reason is, if you put 0 in place of h, you'd get a 0 in both the denominator and the numerator, which is why this expression looked like this. There is a trick for this one. If you look at the numerator, it's a square root then minus a number. I'm going to define something called the conjugate. And in this example here is, you take the expression with the square root, the 1 plus h and the 1, and you switch the sign so it's positive. We call this the conjugate of this, because instead of a minus, we have a plus. What I'll do is multiply this thing to the numerator and the denominator in this limit. our question, our original limit becomes the limit as h goes to 0 of, I'll write the original expression, that's the square root of 1 plus h minus 1 all over h. But I'm going to multiply this fraction essentially by 1. I'm just going to write 1 in a pretty complicated way. I'm going to put the conjugate in the numerator of this fraction and also in the denominator. So this fraction, it definitely equals 1, so multiplying it to this limit does not change its value. But something nice is going to happen when you take an expression like this and multiply it by its conjugate, and we'll do all that work next. So I'll add in some parentheses that'll help aid in this process. To multiply these two things together, we have to distribute. In fact, we have to take this and multiply it to both terms over here. And then we repeat that process with this -1. We multiply this here and here. We're going to have 4 total terms. In the denominator, I'm just going to multiply these two things together, but I will not distribute this h in. And the reason is, at some point, I'm going to want to cancel that h. So this looks like the limit as h goes to 0 of, so my denominator is h times the square root of 1 plus h plus 1. In the top, when I take this and multiply it to this, we're squaring the square root of 1 plus h. So this times this is actually just 1 plus h. That's nice. Okay, now I take this and multiply it to this plus 1. All right, that's not nice, but I'll put plus 1 times the square root of 1 plus h. I then multiply this -1 to the square root of 1 plus h, so I get the negative of this thing, so that's minus the square root of 1 plus h. And then lastly, I have -1 times +1, which is -1. The reason multiplying this by its conjugate is nice is because your middle terms cancel. We have plus this and then minus that, so those two things go away. That'll happen every single time. I'm also going to note that, well, there's a plus and -1, and that cancels too. It really simplifies this nicely to the limit as h goes to 0 of. The denominator is exactly the same because I didn't do anything to change it. And the top is just h. That's the only thing left over. I was hoping to cancel an h over h, and I can. So here I can say, well, this h cancels, and so does that. They're just ones. I can write this whole thing as the limit as h goes to 0 of simply 1 divided by, I don't need the parentheses anymore. I'll put the square root of 1 plus h plus 1. Can you now simply put 0 in place of h to get your answer? Definitely. So I'll continue that work here. If you put 0 in place of h, you get 1 divided by the square root of 1 plus 0 plus 1. That's 1 over 1 plus 1, and the answer is 1/2. There is one more theorem from this section that I'd like to discuss, and let's motivate that by looking at example 8. Here I'm taking the two limits that we started our lesson with, the limit as x approaches 1 of f of x and g of x, and I'm making them both 5, so they're both the same number now. So for this limit, it goes to 5. The limit as we approach 1 of g is also 5. So we have these two functions, f of x and g of x. Let's assume there's a third function. Again, I don't know the formula for it, but there's just some other function out there. And let's say you know that the function f of x is less than or equal to the function h of x, and h of x is less than or equal to the function g of x. With this information, can you figure out what the limit as x approaches 1 of h of x is equal to, if you know this one and this one? So as we approach 1, f of x is going to 5, and so is g of x. And we're basically asking, well, can I get an answer for this? I'm going to try to explain this graphically to figure this out. So I'm going to draw a graph over here, and we're approaching 1. So that's the limit we're approaching. And for both f and g, we get the result of 1, 2, 3, 4, 5. If you say that f of x is ultimately less than g of x, You could draw in an arbitrary function for f that looks like this. So here's the function f. So it has to approach 5, and maybe it does this over here. So this is f of x. Now, g of x is always greater than f of x, but it has to go to this limit as well. So I'll draw that in 2. So this could be your function g. It has to have a limit of 5, and it has to always be greater than or equal to f. So here's g of x. To say that there's this other function that's between them means, well, it's not above, it's not below, but it's like stuck between the two functions. And we're trying to figure out what its limit has to be as we approach 1. So I'll draw what that function would have to look like. So here's h of x. It's got to be between the two functions. This is always true, including at this spot here. And then it has to pass through, and maybe it looks something like this. Is it clear what the limit as x approaches 1 of h of x has to be? It has to be 5. And the reason is this is squeezed to this value of 5 at x is equal to 1 if h is always between f and g. There's a name for this theorem. It's called the squeeze theorem for the reason I just stated here. I'll place that theorem on the next slide, and we'll apply it in one example. So to state the squeeze theorem, it says that if you have three functions, f, h, and g, and f is less than or equal to h of x is less than or equal to g of x, if you know the limits of f and g as we approach the number a are equal, so this limit is the same as this one, then the limit of h has to equal that value as well. So here in example 9, we're going to assume that 8x is less than or equal to h of x is less than or equal to 4x to the fourth minus 4x squared plus 8. Can we use this information to figure out what the limit as x approaches 1 of h is equal to? If you want to use this theorem, you have to be careful. You have to make sure that we're satisfying all the assumptions before we can state the conclusion. So for this, I'm going to let f of x equal 8x and g of x equal 4x to the fourth minus 4x squared plus 8x. So first, is it true that f of x is less than or equal to h of x is less than or equal to g of x? Yeah, that follows from this statement here. We're basically just saying that this is true. So I'll say, I want to note, it should just be note that f of x is less than or equal to h of x is less than or equal to g of x. And this is actually for all x. Next, what is the limit as x approaches 1, that's the limit I want to consider, of the function f of x? Well, that's the limit as x approaches 1 of 8x, and that's equal to 8 times 1, which is 8. We also have that the limit as x approaches 1 of g of x is equal to the limit as x approaches 1 of, so that's 4x to the fourth minus 4x squared plus 8x. What's that limit? It's actually also 8. You get 4 times 1 to the fourth minus 4 times 1 squared plus 8 times 1, which is also 8. As this limit is equal to this limit, by the squeeze theorem, g has to have the same limit. So I'll say, as the limit as x approaches 1 of f of x equals the limit as x approaches 1 of g of x is equal to 8, by the squeeze theorem, the limit as x approaches 1 of h of x, whatever that formula is, has to be equal to 8 as well. When applying any theorem, it's very good to follow the logic of the theorem itself. By that I mean, you want to set things up so you're showing that all of the assumptions, the beginning portion of the theorem is true, and then you want to state the theorem and the conclusion from it.